On Monday, we were doing some calculations that may have seemed a little gnarly to you. We were using ice tables and a solver to find x. And we will not have to use a solver for all of these problems. There are some times when we can make an approximation that greatly simplifies the calculation without affecting the accuracy of the result. And so we're going to learn when we can use that approximation. And so, like, most of the exam questions will not require the use of a solver. And they'll not require the use of the quadratic equation either. But you need to know how to apply the approximation and identify whether it is appropriate or not. So, if K, the equilibrium constant, is very small, that means that the reaction doesn't proceed very far to the right. It only goes a little bit. And so if we have initial reactant concentrations that are relatively large, then the amount that they decrease, which we've been calling X, is going to be small. It's going to be small in comparison, and so small, in fact, that the reactant concentration is essentially unchanged, and so we can leave X out in those places. We will check that assumption by comparing the calculated value of X that we end up with to the number that it was subtracted from, and if this is 5% or less, then this approximation is valid. So I think a lot of people are bothered by the fact that you can take a number and subtract something from it and say, well, it's the same number. Does that bother you? I mean, it's like, well, how? Okay, so I live in Reedley, so fruit trucks, okay? We grow like most of the world's stone fruit. So we got these semi-trucks all the time going through with loads of oranges and nectarines and various things. And there's a scale in town, and they go and they weigh, right? Because they need to know how big their load is. I don't know how much these trucks weigh, but it's definitely tons, multiple tons, right? So let's imagine a semi-truck with a load full of peaches, right? And it pulls on to the scale, and they weigh it, and then as they're leaving, one of the peaches falls off. Do they need to go back and weigh the truck again? No, because the mass of that peach is so small in comparison to the whole load that it just doesn't matter at all, right? So that's the sort of thing that we're talking about here. If we're subtracting something that is very small in comparison to the whole thing, it really has no effect. Okay, let's look at this one. So here we have our reaction A goes to 2B, and here's our equilibrium constant, times 10 to the minus 5. So this is pretty small. Initial concentrations are 1 molar and 0 molar. What are the equilibrium concentrations? So we're going to follow the same steps. We're going to make an ice table. We're going to put in the initial concentrations. We're going to look at the stoichiometry and say, well, how are these things changing? Well, the reactant started with some concentration, so it's going to go down. The product was 0, it can only go up, right? So this is going to go down by X, and this is going to increase by 2X, and that 2 is because of this coefficient 2. So then we take our initial and change rows and we add them together. We have 1 minus X, and we have 2X over here. So we can write the equilibrium constant expression, right? It's B squared divided by A. And we can plug these numbers in. 3.3 times 10 to the minus 5 is equal to 2x, the quantity squared, divided by 1 minus x. So the X is small approximation says, well, this is a small equilibrium constant. This is a large concentration. For the stuff that we do, 1 molar is pretty concentrated. Small would be like 0.0001 molar, okay? Just so you have an idea of what we mean by big and small concentrations. So X is going to be small, and so this is like that truck full of peaches, and it's losing 1 peach. If X is small, then subtracting it from 1 doesn't change anything. So the X is small approximation, then we can say, well, that's essentially 0. It's so small relative to what we're subtracting it from that we're not even going to bother with it. Well, how does that help us? Well, now we only have X here. And so instead of a quadratic equation, we're going to end up with x squared equals something. We take the square root, and regular algebra saves the day. You can still use your solver if you want to. No problem with that. So this x, we're saying, is essentially 0 relative to this. Can we make this x 0 as well? No, because here we're looking at 2 peaches, not being subtracted from something, but just the mass of 2 peaches. And it doesn't matter if they're very, very small. That's all we have. That is significant. So the x is small approximation. We're going to take any x's that are added or subtracted in this, and we're going to make them essentially be 0. But x's that are not added or subtracted, we have to keep. Okay? So let's solve this equation then. And again, using the solver is absolutely fine. This denominator is 1, right? And so I'm just going to flip it around. 2x squared is equal to 3.3 times 10 to the minus 5. To get rid of the square, I'm going to do the square root of both sides. So now I've got 2x is the square root of 3.3 times 10 to the minus 5. And I divide both sides by 2. So I'll get out the calculator. Square root of 3.3, AE minus 5, divided by 2. So x is equal to 0.002872. To check if this is valid to do this, we're going to take this x that we came up with, and we're going to compare it to the number that it's being subtracted from. We want to know what percentage of 1 is this number. So the percent is going to be 0.002872 divided by the number we're subtracting it from times 100. And that's going to be 0.2872%, which is definitely less than 5%. If we think about significant figures, we've got 1.0 and we're subtracting 0.002872. All of these fall into no man's land, right? This 0 was uncertain. So we can do that subtraction on the calculator, 1 minus that number, and we can get an answer. We're going to get 0.997128. But the uncertain digit is in the first can't see that very well, in the first decimal place. If we round this to the first decimal place, what do we get? 1.0. Because this is like the peach that fell off the truck full of peaches. We're not even going to miss it. If you go back to the scale and reweigh the truck, it's going to say the same thing. So in final concentrations, equilibrium concentrations, I've kind of made a mess here. I'll sort of squeeze it in here. So the equilibrium concentration of A is going to be the same as what it was to start with. The equilibrium concentration of B is going to be 2 times the X that we found. Zero 0.00575, and well, that looks like a lowercase delta. That's not good. That's supposed to be a 5. And so I would round that to 0.0000. That's a better 0.006. And that's molar. This is a small number, but it's not 0, right? But if we subtract a number like this from 1, it really doesn't matter. Does anybody have any questions about that? Because that's kind of a thing you have to get past in your mind. Yeah.
So on the test, if we solve using 1 minus x, would we get the wrong answer then? Like, are we supposed to intentionally move like that?
That's a great question. So if we didn't use the x's small approximation, would we get the wrong answer? Let's find out. So I'm going to take this like we did on Monday, and I'm going to type it into my solver and see what we get that way. So 3.3 times 10 to the minus 5. And over here we have the quantity 2x squared divided by 1 minus x. I'll put this in orange. So without using the approximation, I get x is equal to 0.002868. Pretty close, right? You multiply that by 2, let's see. You get 0.0057. You round that to 0.006, it's the same. Now, sometimes, because this is less than 1% difference, sometimes when it's closer to 5%, you may have one little difference in the uncertain digit, right? But that happens, there's uncertainty. So, great question. Any other questions? Okay, let's do a more real example. So here we have the decomposition of hydrogen disulfide, balanced chemical equation. Here we have our equilibrium constant. Is this a small equilibrium constant? Yes, it is. So our reaction mixture, here we're given some initial concentrations, and we're asked to find the equilibrium concentration of S2. So we're going to make an ice table. So I'm going to use the balanced chemical equation as the header. and then I'm going to have I, C, E. I'm going to start doing that in a different color. I, C, E. Okay, there's our ice table. We take the initial concentrations and we write them in. So H2S, 0.100. Our concentrations have to be in molarity, and so we don't really have to write them in here. We just need to make sure that we always use molarity. And we're told that the H2 concentration is 0.10 also, and that the sulfur is 0. So I think this is the first example where we've had reactant and product concentrations at the beginning. So when we look at this and are trying to identify the change, we need to decide, well, which side is going to lose and which side is going to gain. We could calculate the reaction quotient, and that would tell us. Many times we can just look at it and figure it out. Could this lose any concentration starting at 0? No. That cannot go any lower. The only thing it can do is go up, right? So this has to be plus X. So everything on this side of the reaction arrow is going to have the same sign. So that goes up, this has to go up. How much does this one go up? 2x. So this is going up by 2x. And then everything on the other side must be decreasing. So how much is the H2S decreasing by? 2x. So this is minus 2x. These individual steps aren't hard, but there's a lot of them, and it's really easy to get lost. Like I mentioned before, we're going to be doing ice tables a lot. It's not just this chapter. There's at least 2, maybe 3 other chapters that have ice tables in them. So I don't want to lose anybody right now, because you can all do this. You just may need to ask me some questions if it's not making sense to you, okay? I'd love it if you ask it in class, but if you don't want to do that, come and ask me afterwards. Okay, what's the next step? We're going to add them together. So we're going to pretend that's our adding line, right? And so we've got the initial plus the change gives us the equilibrium value, 0.100 minus 2x. This is 0.100 plus 2x, and this one is just x. We're going to write our equilibrium constant expression from the chemical equation. We're going to have H2 squared times S2 divided by H2S squared. Now we're going to put our equilibrium constant, 1.67 times 10 to the minus 7, and these expressions into that we could plug this into a solver, but we can also use the X is small approximation, and it's actually going to be faster than the solver. We have a small equilibrium constant. These numbers are relatively large. Let's try the approximation. So if X is like a peach that fell off the big truck, losing 2 peaches or gaining 2 peaches not going to make any difference in the mass of the whole truck, right? So we're going to say, well, that is 0, and then this is 0. They are so small that adding or subtracting them to 0.1 isn't going to make any difference. You can only get rid of x's that are being added or subtracted. You can't get rid of this x, because then that would be saying that all of this is 0, and 0 does not equal that number, right? When we get rid of those two terms, though, now we have 0.1 squared divided by 0.1 squared, and that cancels out. And so our answer is x is equal to 1.67 times 10 to the minus 7. We're like, well, that was too easy. No, that's just what it is. So that is equal to the sulfur concentration at equilibrium. We always should check the 5% thing. So x came out to be 1.67 times 10 to the minus 7. If we divide that by what we're adding or subtracting it from, the 0.1, and multiply by 100. And you don't actually have to do the math. You can look at that and say, oh, that's going to be less than 5%, but I'm going to do the math. It's much, much less than 1%. It's 0.000167%. So the x is small approximation is valid. And let's put an m in here. And this is our answer. What is the equilibrium concentration of S2? Any questions? Yeah.
If the initial concentrations for H2S and H2 were different, would you still divide by 0.1? Like how would you
Good question. So what if these were different? I'm going to divide by whichever one is the smallest, whichever one it would have the biggest impact on. I'm looking to find the highest percent that I can given the numbers I've got. Great question. Any other questions? Here's another one. No, that looks like the same thing. No, it isn't the same thing. It looks the same, but the initial concentration is different, right? I don't know if this will work. Cool. Okay, through the magic of technology, there's my table from the previous one. So what's different here are the initial concentrations. I'll just erase all of them. So our initial concentrations are different, but the changes are the same. So now H2S starts at 1 times 10 to the minus 4. And H2 and sulfur are both 0. So this is 1.00 times 10 to the minus 4 minus 2x. Oh, well, that Funny things happen sometimes. So I kind of cheated. Does that make sense to everybody? It's the same chemical reaction. Our products here are both 0. They have to go up. They can't go down. So this side is plus. This is plus 2x because of the coefficient of 2. This is plus x. This is minus 2x because of the coefficient of 2. We add the first 2 rows together to get the bottom row. The expression is also the same. And so then we're going to plug our numbers in. 1.67 times 10 to the minus 4 is equal to, okay, so H2 squared, that's 2x, the quantity squared. And then we've got x for the sulfur. And this is divided by 1.00 times 10 to the minus 4 minus 2x. And that is squared. Yes, it is. Thank you. I'm not sure where I got that from. Maybe from here. This is supposed to be a 7. Thanks for catching that. Well, here we have a small equilibrium constant, but now our starting concentration is a lot smaller, right? Let's give it a shot. Let's just try the X is small approximation anyway. I mean, what could it hurt? And we have to do it the long way? Well, we may have to do that anyway, but... So if we say that that goes to 0, what do we have then? We've got 1.67 times 10 to the minus 7 is equal to... So the quantity 2x squared is 4x squared, right? And then we're multiplying by another x. So this is 4x cubed up here. And then this is 1 times 10 to the minus 4 squared. So I'm just going to fast forward here. 1.67 times 10 to the minus 7 times 1.00 times 10 to the minus 4, the quantity squared. And that's divided by 4. And we take the cube root of that. And you're thinking, oh, this looks like we might as well just use a solver on the whole thing anyway. Yeah, sometimes they're like that. 1.67 AE minus 7 times 1 AE minus 4 squared divided by 4. Oh, shoot. I deleted the wrong row. I get to start over. Okay. Oh, let's do that. Cube root of 1.67 times 10 to the minus 7 times 1 AE minus 4 squared divided by 4. Anybody else get that? This is where you definitely want to check your math because it's so easy to make mistakes there. if I do the check on this, and I take my x and I divide it by the thing that I was going to add or subtract it to, and multiply by 100, I get 7.5%. That's too big. This is not valid. We can't use the x is small approximation. So I'm going to type this into my number solver then, with all of the x's. Okay, so we just paused, dear YouTube people, and used the solver to find out what x would be. And we got x is equal to 6.781 times 10 to the minus 6. Yeah. Now, those of you that are taking notes, what did we come up with for the x is small approximation? So we get 6.78 times 10 to the minus 6, or 7.47 times 10 to the minus 7. So those are different, right? Those are not the same. Looking at that percentage and seeing that our x is small answer here was 7.5% of what we were subtracting it from, tells us it's too big. We can't use x is small. Any questions? X is small used to be super, super important because solving those equations was so tedious. Now that you've got a $25 calculator that can do it for you, do we really need the x is small approximation? Probably not. Because you can always just type the whole thing into your solver and get the answer. And so if you like the solver and you don't want to mess around with the approximation, yeah, you can get an A on the exam and not do the approximations. So did we get the right answer? Yes. Questions? Yeah.
So how do you get there without the calculator?
How do you get the right answer without the calculator? So on this one, because x is small is not valid, you would have to use, well, I don't even know what you would do because that ended up with an x cubed. You could not solve this one without some sort of a number solver. I will not give you questions like that on an exam, okay? They don't have them in the test bank. Yeah, but that's a good question. So the x is small approximation was really, really important before we had computers. So here we have a generic reaction, A goes to B. We've got different values of the equilibrium constant and initial concentrations. For which set of values does the x is small approximation most likely apply? Not going to do the calculation. Do we want k to be big or small? We want k to be small because that means it's not going to go forward very much, meaning x is going to be smaller. So we've got 10 to the minus 5 and 10 to the minus 2. 10 to the minus 2 is bigger, and so it's not one of these. So we've chosen the one with the smaller k. And if the concentration is higher or lower, which is better for x is small? Higher, right? Because when we're subtracting a number from 0.25, it's more likely to be less than 5% of it than from 0.0025. So this is the answer, most likely to apply. Any questions? So just some notes. Concentrations have to be in moles per liter. There could be a question on an exam that tries to trick you like that. There was a homework question someone was asking me about yesterday where it gave the volume of the container or the solution, and then it gave the moles of everything. And it's real tempting to just take the moles and put them into the ice table and solve it, and you get the wrong answer. It has to be done with molarity, okay? If we're doing pressures, the partial pressures have to be in atmospheres. If they're given in millimeters of mercury or something else, you have to convert them. We need to use the appropriate equilibrium constant, Kp if we're dealing with pressures, Kc if we're dealing with concentrations. You cannot mix and match. You can't put concentrations and pressures together in an equilibrium expression. Moles can be used only when the moles of reactants in the chemical equation is equal to the moles of products. This is a very small percentage of the time. So I would just say, we can't use moles. Just say you can't use moles. This is the fine print. There are times when you can, but if we just don't try, we'll always be correct. And then it's important to remember the x is small approximation does not mean that x is 0. It means that x is so small that if we add or subtract it to this other number, it doesn't make any difference, and so we can skip it. Okay?